We now look at a comparator. This is a 4-bit comparator. The purpose is to compare two 4-bit strings and determine if they're equal. The strings are A and B, and we see in the circuit A0, A1, A2, and A3 are compared with B0, B1, B2, and B3. If the strings are pairwise equal, if each corresponding bit is equal to the bit in the other string, the output is 1, indicating equality. If, however, one of them is unequal, or several of them are unequal for that matter, the output is 0. And here we've got a case where there's 2 bits, A0 and B, it doesn't match B0, and A3 doesn't match B0. The answer is false. They're not equal. However, if I go back to the original state, they are equal. Likewise, if these are both 0, that's fine. Everything's equal. These are both 0, everything's equal. It works. This is an exclusive OR. Exclusive ORs are similar to regular ORs, but they are slightly different. An exclusive OR is A or B, but not both, whereas an inclusive OR is A or B and both. What do I mean by that? It means in an exclusive OR, if either A or B is true, the output is true. If they're both false or they're both true, the output is false. A or B, but not both. A regular OR, sometimes referred to as an inclusive OR, is A or B and both. If either A or B is true, or if they're both true, the result is true. This is a regular OR, this is an exclusive OR. And with the exclusive OR, you can see what's going on. If I get a well, let's go this way. If they're both 0, the output is 0, and it comes down here. This is a NOR gate. See the little circle? It's a NOR gate, which means if all of the inputs are false, the output is true. If any one of the inputs goes true, the output goes false. It's a NOR gate. It's an OR gate with a NOT at the end of it. All right, so we can see here in this situation, first of all, if they're both 0, that's false. If they're both 1, it's false, because they are both equal. If they're mixed, however, it's true, and that becomes a false after going through the NOR gate. Basically NOTs, whatever the inputs are. So that's how it works. Fairly simple, fairly clever, and it can be extended. You can just add more of these as you want. This, of course, is the exclusive OR gate, and you can see if either one of them is on, the output is on. If they're both on, the output is off. Exclusive OR is not a fundamental gate. It can be built up. Here is how you can build. It's one way of building an exclusive OR out of ANDs and ORs. And, of course, it can also be built from NANDs or NORs, as we showed earlier, because they're sufficient. And you can see this is functioning like an exclusive OR. If they're both off, the answer is false. If either one of them is on, the output is true. If they're both on, the output is false. So this is an exclusive OR.